kind of give you some perspective on what we're talking about when we talk about NMOS transistors and PMOS transistors and gates and sources and drains, and kind of get this down like the 22 nanometer level, how difficult that can be. Because you gotta lay it down and you gotta do all of the lighting lithography in order to create the source and the drain. And you have to actually, input the impurities. And you have to do this all very precisely. It has to be very clean too, because you saw people walking around. They'll say that the fabrication rooms in most foundries are actually 100 to 1,000 times cleaner than a typical hospital, because you get one piece of dust in there and the whole wafer is screwed. So that causes issues. So anyway, I wanted to go over 1.4. So this is a kind of a review of what we were doing yesterday. But I think this is a good combination of taking a look at how creating a pull-down network and creating a pull-up network and then putting them together and then using the De Morgan tools will actually help you do this faster. So the general idea is that we have F equals not D or A and B or C, right? So when it's not, you can just start out. So we know it's all negated, so it's going to pass that last rule, right? So what we do is we look here at the pull-down network, and you know that ores are in parallel. So right off the bat, we start B or C, right? Are in parallel. That goes to ground. And then it's ANDed with A, so the pull-down network ANDs are in parallel. So this, we put A here, and again, we have D or with the quantity, so that means that D is in parallel. Does that make sense? So then the next step is to perform the De Morgans. So D and, that's going to be negated, so A, B. But from there, it's going to become A not or not B or C, and that becomes A not or not B and not C. Right? So now we just follow this map to create a pull-up network. So then we know that A or C are B and C are in series, right? So we can do this. B, C, and then we know it's in parallel with A. And then you can do one of two things here. You can either put D here, like so, or you can put E down here. Right? Either of those work. It's logically equivalent. So that makes sense how we kind of did this 1.4 here. So the first step I've shown is this is the pull-down network. We performed the De Morgan's law, and then we did the pull-up network. Now, on an exam.
So,
I'm sorry. Yes.
So for pull down and pull up networks, whenever they're ANDed in some series, for both of them.
Yeah. So here we have, that's why we do it, so that we can switch around the pull down and pull up characteristics. We have B or C here, right? They're in series here, but they were ordered up here, so they're in parallel. So by doing the Murray's law, we split them back and forth. So the big question is, what do I need to put on the exam in order to ensure that I get full credit, right? So this is the full credit solution, right? Now, if you want to get partial credit, you also should write down what your De Morgan is. Because if you make a mistake in your De Morgan, and then what you write in your De Morgan translates to your pull-up network properly, I'll write something, for those of you who haven't had English, Professor Joe called error carry forward. If you make a mistake in your De Morgan's law and that translates to your transistor, I'll give you credit for the transistor. You probably take off just 1 point for making a mistake on De Morgan. Okay. So, That's what I like to say. Give me a reason and give me points.
Does anybody have any questions about that? Okay, so I should also mention that grad 1.2 / extra credit that the undergrads seem to be passing on. This is just basically a 5-minute video of the same thing, except it's a 22 nanometer process, and how the FinFETs are fabricated slightly differently. And it's just one paragraph on the difference between that and what we watched today in class. Okay, before I go on, one last sentence. Anybody have any questions on this? Yes.
It uses the same wording on this. It says perform De Morgan's laws on the equation used to result for the pull-up network.
Yeah.
So the pull-up network isn't the PMOS.
Yeah, the pull-up network is CMOS. Pull-down is NMOS. So what you want to do is you start with the original equation, right? Let's negate it. Which is what we did here. So that already that step by step. So this is the original equation here. D or quantity A and B or C. So since it's negated, it's going to satisfy that rule that we're allowed to just do it. If it's not negated, you can just negate it and then put an inverter on the end. But since we have it negated, we can do it fine. So we start with the pull-down network, which is up here.
So we start with this equation, and since ORs are in parallel, ANDs are in series for NMOS, which means D or, so this actually reads just like the equation, D or quantity A and B or C. See? Then we do the De Morgan, which is the exact same equation, it's just doing De Morgan's laws to do a map for the PMOS. So here, we complete it, it's D and A quantity A or not B, not C, right? So this means we can just follow the map. So it's D and quantity A or B, C. And if you notice, it's gonna be the exact, when I say the exact opposite for the pull down and pull up network, this means is like, see how this D is in parallel with this? It's gonna be in series in the pull up network. A was in series with B or C. That means it's going to be in parallel with B or C. B or C were in parallel in the pull-down network. That means they're going to be in series in the pull-up network. That's the reason why we do the De Morgan's, is to help you flip it.
So when we did the TGO yesterday, I think what confused me is that I had the PMOS backwards, and it said inputs and ANDed together were in parallel.
Right.
Okay, so that's right. They're both supposed to be the same. NMOS and PMOS.
Mm-hmm. Yeah, so you can do one of two things. All right, so there's two different methods. You can either lose track of what's on the screen, or, okay, so you can either not do De Morgan and just flip it, right? I'm going to pretend they're not. You can either do the De Morgans and just flip it around. So you can not do the De Morgans and just flip it around and put them in parallel, or you can use the De Morgans and just follow the map. Yeah. So there's whatever way you feel more comfortable with.
Okay, so that's what it was talking about. How if you can't do it, you invert it.
Yes.
And you invert it. Okay.
Right. So what happens is if you have just a positive, there's going to be instances where we can't create the proper output. So but if we do this pull-down network and invert, then we can just do this and then just invert the output. So that's why we did the AND for the first example. I worked that whole last class about how you can't do AND gates by just flipping them around because the zeros and ones, we can't, the strong, how NMOS or PMOS are strong zeros and NMOS are strong ones, so therefore we can just flip them around. So then we just keep that principle and just inverts the outputs. And as we'll learn later in the course, you can actually manipulate the width of the transistor for the inverter on the output in order to restore the signal. So if you start seeing this degraded signals, you can use the inverters as a kind of a buffer to restore. Well, that's, I believe, buttoned for the moment. Any other questions? Okay. So we just watched this video on how CMOS transistors are fabricated. So what we're going to be using in this course when we describe the different stages, we're going to talk about N-well and polysilicon. Now here I say 20 angstrom because it's a specific type of technology. And the polysilicon, if we go back to the transistor earlier, the poly is actually going to represent the pin. So actually we had these over here. So we have the SiO2, we've got your glass, your silicon oxide, and then you have your poly. The polysilicon is actually what's being used to transmit the signal. So we have our A and B inputs, and this is kind of obnoxious. There we go. So anyway, our polysilicon, and then we have metal. When we're talking about metal, metal is what connects everything together. Now, to answer a question you were asking last class about the silicon oxide kind of surrounding everything, we're going to be talking about something called gate capacitance, where we're actually going to be having charges based on the difference between the channel and the polysilicon. You see how there's a width there? The channel is going to represent one plate of the capacitor, and the polysilicon is going to represent the other plate. So we're actually going to be using this thickness of this oxide to be able to calculate the gate capacitance. And so, that gives you questions. Like, it's the same thing with the metal for the output for Y, and then again we're going to be creating this gate out.
So the N diffusion and the P diffusion is where they were bombarded with the electrons.
Exactly right. Exactly right.
And
so when they're bombarding the electrons they're creating, the first thing they're going to do is they're going to create this N-well. That's the first step, and then the next stage is they're creating these N and P plus ions there. Like we were talking about boron and arsenic at the beginning of the lecture, that's what they're bombarding with. And so the whole point of laying down the lacquer and etching it is in order to make these measurements here at the transistor very precise. And to make sure that they don't overlap. We're going to be learning about what they call parasitic capacitance. Like I was talking about here, about how we have this gap here. Well, what happens when the channel doesn't quite make it, suddenly we have this gap here. You just created another capacitor. And that's, you have a capacitor in an instance where you don't want the circuit working, so you get this thing called leakage current. Oh, but again, all I believe buttons. I should have just said yes and moved on. Okay, so we're going to be learning about contacts. Contacts are where you're actually going to connect the inputs to the transistors. So you're going to get this input signal from the pad frame. It's going to go to a specific input there. And last but certainly not least, metal. So to read the 6 types of fundamental masks in CMOS: N-well, polysilicon, N plus diffusion, P plus diffusion, contacts, and metals. And I'm going to scroll down a little bit. So in these diagrams, you're going to see the N-well is where we initially have our PMOS transistor, because we're going to put our P plus diffusions here for our source and drain. And then polysilicon, this is actually connected because we're going to build the inverter. You're going to actually see how it works. Using here's the inverter, here's the inverter. And then we have our N plus diffusion, P plus diffusion. We have our different contacts for our source and our drain, or VDD. And then our inputs and outputs, and then metal is where the actual carriers are going to be going through. Once you get out, then you get potential, and that's going to flow through the metal. So that's where our zeros and ones between our gates are going to flow. And so another aspect of this polysilicon is that the width of the polysilicon relates to something called feature size. So if you ever heard of like 22 nanometer technology, 0.3 micron technology, and all that, that 22 nanometer relates to the width of the polysilicon. So we actually define feature size as the distance between the source and the drain. It is set by the minimum width of the polysilicon. And kind of go back, for perspective, this would be the size of the transistor if it was 0.13 microns. And then this right here, that's the size of the transistor at 22 nanometer. So that's over the course of a few generations. We have 0.13, then we have 90 nanometers, 65 nanometers, 45 nanometers, 32 nanometers, 22 nanometers. So it's getting smaller and smaller and smaller and smaller. And this next chart will illustrate that even further because it actually, you notice it goes along very well with Moore's law. So back in the, when we created the first transistor here, does anybody remember the name of the guy who did the first transistor? Gilby. Gilby was one of them. Who's the other one? Oh, Gilby did first integrated circuit. John Jordan. VLSI. So this is the side of it. You can actually see it on the screen. Now we're going all the way down 0.35 microns, 0.25 microns, and we're it down to, and Intel's right now here doing 22 nanometer with their ivory bridge tri-gates.
They're working on 14.
Yeah, they're working on 14. Everybody's working on the next one, so they're trying to get down to 14, and some were even playing with like 9 nanometers. And of course, yes, they magically knew. So this is just a news article. Intel's 14 nanometer revolution, why you should care. And here you go. Width of the polysilicon. Right there. So as it's getting smaller, you're going to deal with different issues. And when you think about it, as everything gets smaller and smaller, you have to worry about channels, you have to worry about enough space for the electrons to actually create a channel. You're going to be worrying about all these different capacitances, which eventually translates to power. We're going to be learning about dynamic power next section, and that's actually dynamic power is what happens is the power consumed when you're switching from 0 to 1, and it's directly proportional to the capacitance. So we have to worry about these kinds of things. Okay, so this is going to be really important for you to know, these Lambda-based design rules. These are the rules that are used in the textbook and in pretty much every simulator, including Logic VLSI Design Lab, which is one of the tools we'll be learning using in this course. So, Lambda, the notation Lambda, is equivalent to half of the feature size. So all these measurements, so say we have 90 nanometers, lambda that now is 45 nanometers, that's your lambda. So then the first rule is by definition, the polysilicon must be 2 times lambda, which I know sounds like, the Department of Redundancy department. But when we get to measurables of contacts and other elements of the transistor, that's where having that half value is going to become important. So, and then we're going to walk through an example. First, we're going to go through how we calculate different sizes, and then I'm going to actually show you an actual CMOS transistor. I have a layout of the transistor, and then in the second half, I'll show you an actual how each of these rules is contributing to the actual layout, to the actual size. So, rule number 1 is by definition, polysilicon must be 2 lambda. Number 2, metal diffusion must have a minimum width and spacing of 4 lambda. So any metals that are running parallel to each other must be 4 lambda apart. So if it's 90 nanometers, they must be 180 nanometers apart. And the other good thing about having this lambda is that once you put in the technology and you put in the design rules, it'll actually measure it on the layout by lambdas. So if you know that the easiest 4 lambda apart is to 1, 2, 3, 4. And they put your next lambda metal over. So rule number 3, contacts are 2 lambda by 2 lambda and must be surrounded by 1 lambda on the layers above and below. So you're going to have, the whole point of a contact is you have some sort of signal in one metal or in one element type. And then you have a different type of metal, or polysilicon, and you have to have them transit somehow. That's the purpose of the contact. You have to make sure that you're going to have a 2 by 2, okay, contact. And then on the outside, you have additional 1 by 1, where you have your metal and polysilicon. So if you have poly, it'll come out like that, and then you have metal here. That way it allows it to actually allow the electron diffusion to continue. Rule number 4. Polysilicon overlaps diffusion by 2 lambda where a transistor is desired and has a spacing of 1 lambda where no transistor is desired. So basically this means that when it's inside the transistor, we want to keep the signals as separate as possible. But if it's not a transistor, we want to try to get the polysilicon from one transistor to the other. Right? And so the result is we only have to worry about that signal right next to it. I don't know where I'm going. Wait a second. So that's why the difference in the rule. Rule 5, polysilicon on contacts have a spacing of 3 lambda from other polysilicon or contacts. And then last, the N-well surrounds the PMOS transistor by 6 lambda and avoids NMOS by 6 lambda. So we're going to have this kind of N-well here, right? And then you're going to have, inside you're going to have your PMOS transistor. And then what's going to happen is you're going to have these polysilicon running here. You're going to have contacts. And here your NMOS, you got 6 lambda. And then it needs to be 6 lambda away as well. And then, you're going to see throughout the rest of the textbook, and you're going to see this thing called WL. I mean, it's pretty intuitive, and you'd be surprised how many people don't know what that means. It means it's just the width-length ratio. And this becomes very important because being able to size a transistor impacts the ability to, like, well, think about if you have, right, polysilicon, right? If you're drawing out the length and the channel gets longer, it's going to require more of a voltage on the gate in order to be able to create the channel. So these length and width ratios, say that 10 times fast. Width length ratios become important in CMOS. So we're going to go into a quick example. Using lambda-based rules with a feature size of 90 nanometers, what is the width and length of the transistor? So remember, we have lambda, which is equal to half of the feature size. That's 45 nanometers. By definition, the polysilicon must be 2 lambda, so that's 90. So metal and diffusion have a minimum width and spacing of 4 lambda. So now we have 90 divided by 2 is 45, right? So the width is going to be 45 times 2, and the width is going to be 40 times 5 times 4. So this becomes 180, this becomes 90. So in your basic rule, you can see the width-length ratio becomes 2 to 1 initially.
The length always be smaller than the width.
Yes. Anybody have any questions? The next thing we're going to do is we're going to be going over that inverter. So if you have any questions about the intricacies of these 6 rules, hopefully I'll be able to address them in a minute here. All the people outside having fun taunting you guys. Okay, so while you guys are still finishing up 1.5, maybe this is an example of a contact. We have the contact inside, it's 2 lambda by 2 lambda, and then it has the 1 lambda around it, like the rule says. And then next we're going to talk about metal and diffusion. Again, you can kind of see down here, I'm going to scroll up just a little bit. Any metal, and the reason why it's denoted as metal 1, when we get into actual layout of these kind of chips, you're going to see that metal 1, metal 2, metal 3, metal 4, because you have metal, those rules are individual metals. Well, let's say you have metal 2, you can just create contact and then circumvent that rule by using the second metal type. Does that make sense? So that's why here it says metal 1. This is a figure from the textbook. So the width of the metal, or the width of the diffusion region, is 4 lambda. So you can see the contact is only half of that. And then we have the space between them is also going to be 4 lambda. And this just becomes important because you're going to have your input, you have a contact, you're going to have some sort of, based on whether or not it's 0 or 1, you're going to have your contacts in your PMOS and NMOS, and based on that, you're going to have an output metal. That output metal. So that's kind of the fundamentals of how an inverter is built, is right here. Okay, so then this is an example of when the polysilicon are in the transistor. So if we're building a NAND gate, I can zoom in a little bit here. Oh, one more. Okay, so this is a polysilicon. The polysilicon, by definition, is 2 lambda because that's the feature size. And then when it's in the transistor, they're going to be 3 lambda apart. So this is where we're going to be doing stick diagrams next. And so when you do the stick diagrams, what's red is going to be up and down representations of the inputs. And that's what's going to be polysilicon. And like we mentioned before, polysilicon and contacts have 3 lambda from all the polysilicon. And then if they're outside of the transistor and they're just being run to another cell, so we're going to be building cells. We're inside the transistor, but then you have outputs and they're run into another cell. You only want 1 lambda apart. And I kind of made an illusion. Later in the course, we're going to be talking about width-length ratios and how that affects our ability to restore transistor signals. But in the meantime, PMOS and NMOS, they have a width-length ratio. So if you recall, we just derived that NMOS as a 4:2 ratio, so that PMOS is going to become 8:2. And later in the course, I will prove why that is. So I've restated the rules, and now I'm going to have this is an actual CMOS inverter. And so on the left is just the inverter itself, and on the right is the notation with all of the different rules. So here we have contacts. The PMOS to NMOS ratio is 2:1, which means you're going to have 2:1 here. And if you recall, so you have 4, 8, right? And as opposed to 2. So that's where the numbers come from. So those numbers we derived, so if this is a 90 nanometer technology, this would be 4590, 4590, 35180. And then this becomes 360 because it's multiplied by 2. So here, it's going to overlap the metal by 2 lambda. And as you can see here, we have this is rule 4, polysilicon overlaps the diffusion by 2 lambda. So this is the diffusion region, so it's going to overlap it by 2 lambda. see this little knob here? That's the overlap. So that's rule 4. So then you have rule 1. This is 2 lambda. Then we have the contacts rule. So each contact is going to be 2 by 2, and then it's going to be surrounded by 1 lambda with each metal. So then this rule here, 6 lambda, from the metal to the end of the diffusion region, this is the end well for our PMOS transistor. So I should probably explain something else. So we're looking at, this is from the top. The closer we were looking at before, you're looking at from the side. So then we have here, we have our P diffusion, and then we have our N well, and then we have our N diffusion, and then we have our ground and VDD. So here's what happens. You get a 0 on the input. Right? That's what the polysilicon is our input. This metal is going to be our output. You get a 0. Recall that PMOS is a strong conductor of zeros. So now we have that put on the gate. We now have a flow from 1 to the output. So now we've inverted it. Same thing. If we put a 1 here, NMOS is a strong conductor of 1s. PMOS is a poor conductor of 1s, so this gets cut off. This allows the flow from ground, which is 0, to flow through the metal, through the contacts, to the output. Yes, Al?
So the N well and the N diffusion are both made from arsenic, and the P diffusion is made from boron.
Yes, that's right.
Are there other types of CMOS transistors, or is it just the PMOS member?
Oh yeah, it depends on, we're just kind of just doing basic, we're just doing basic stuff in this course. I don't want to get too much into the chemistry. If you want to do that, you can take an electronic materials course and stab your eyes out. But that's, anything that's in the group 3 or group 5 elements, have pros and cons in terms of like, we're going to be learning about electron mobility and electron velocity. And so that's why boron and arsenic tend to be the most commonly chosen. But people are kind of messing around with all kinds of different impurities to try to make these work faster and better. So that's a whole research field. So this 6 lambda is rule 6. Contact emittals, that's rule 3. Rule 1 is the 2 lambda polysilicon. Rule 4 is the 2 lambda overlapping from the metal to the diffusion region. With rule 2, then just dot on it. So yeah, so the width of it is 4 lambda here from the metal. I thought it was really bugs for a second on the screen. So does this all make sense? Okay. Cool deal. All right, so as you can probably imagine, if you're an engineer and you were trying to design something bigger than an inverter, and you have to lay all this out, this can become cumbersome pretty fast, right? As Mr. Leonard will tell you, these people who took the CMOS VLSI course when they had the lab, what did they do for fun when they were doing CMOS?
Drink.
Yeah, that's pretty much it. They would go drink and then come back and do the lab. It's very time intensive. I'm going to teach you a little trick that's going to save you a ton of time. It's called stick diagrams. And yeah, show you drink. Nope. I like being employed. But basically, it's very time consuming to lay that all out. So if you get the stick diagram and then make the stick diagram fit to the rules that we just discussed, then that's going to be very helpful. Stick diagram is a simple way of relating the VDD to the ground, the N diffusion, the P diffusion to the output. So this is the idea of an inverter. So you have an inverter, right? And so that A is your input, and it's going to go to your PMOS, and your VDD, and this is your output, and this is your NMOS, and this also goes there, and your ground, right? So we're going to relate this to that. So what's going to happen is we want a path from VDD to ground. We're going to want a path from VDD to the output, and then want a path from ground to the output. So the first thing you're going to do is you're going to write out your VDD and ground, and your output. Right? So what's going to happen next is you're going to apply poly. Poly is your input here, right? And then you're going to do contacts. Come on, come back. There we go.
The VDD is the gate.
VDD is the supply voltage. That's logic 1, and ground is logic 0. So when you have your N differential, you're going to have that here, that's NMOS, and then your PMOS here, right? So there's multiple ways of doing this. I'm showing you one way, the diagram is showing you a different way. You would create contacts, like so, or the diagram is showing you is to draw it so that you have your voltage here, and then it's going to create a metal here for the output. And then you're going to have your poly. I'm just going to leave these caps on because we're going to be doing other examples here in a minute. Right. So what's going to happen is you're going to have a metal here, right? Metal's going to contact here, and then contact, and the same thing, we're going to have a metal here, and contact, and the output, right? So,
What's green?
green is your N diffusion. So this is your NMOS transistor.
Yeah, what material is that?
That is your N diffusion. That's your N diffusion. That's where you have your negatively typed metal. Yeah. So to relate that to this, you have your flow of metal here. So it's going to flow from here to the output. And it's going to flow from here to here to the output for 1. If it's a 0, it's going to flow from there to there. And the stick diagram is useful because before you have any of those 6 rules that we were just talking about earlier, you can actually lay out the actual flow of the circuit. And then you just make the flow of the circuit match the rules, and then you produce your circuit. The problem that most designers have, and what I was trying to get Kevin to say instead of drinking, was that they don't lay these out. When you just try to put things together, you don't know what's going on. It'll take you hours and hours and hours and hours and hours. If you do this properly, and then you just make it fit the design rules, then it'll take you like 30 minutes instead of 7 hours. So hopefully this saves you, well, this should save you some time because it's on the lab, so I'm going to actually ask you to do them. So we're going to be doing a step-by-step process. So there's a 5-step process to drawing any of these diagrams bigger than an inverter. The first step is to draw a path for your flow. We're going to call these path diagrams. So we're going to be building off of the previous problem we did. This path diagram here is like a path from VDD to the output. So for 1.4, if you recall, example 1.6 is kind of the same as example 1.4 from earlier. We had that same equation, not D or A and B or C. So we want to go from V out. Let's go over here. So we have V out, and then VDD and then out, right? So the first way to do it is you can just go straight from D, and then you have to go through A, and then or B, or C, right? So those are any of the paths you can get to go from the supply voltage to the output, right? And the reason it's going to be useful is because when we create the directions for our contacts, the flow has to go through the transistor in order to, so you either have to just go through the D transistor or go through the A and then B or C, right? So we're going to use metal to actually do. So if we actually were doing VDD, right, and then this would go to like, let's just say this is D, and then this is out, right? Or you could have A here, and then B or C, right? And then what happens is you can either flow through B here, or you can go around, right, to C. And we're going to be drawing that out there. So that's to go through A and B to out, or A, C and out. So you want to draw the path diagram for the pull-up network. Oh, sorry, so it says pull-down network and then pull-up network here. So this one's from ground to V out, and then we'll do VDD to out. So then step 3 is kind of the same thing I did earlier here. Draw the sticks, you're going to draw the VDD. You're going to draw P differential, ground, N differential, your poly, and your metal outputs. So step 4, you're going to draw contacts around the poly for the N active for the pull-down network based on a path diagram. And then step 5, draw the contacts around the poly for the P active for the pull-up network. And when we go through this example, hopefully it'll all make sense. There you go. Okay, so the first steps are the pull-up and pull-down network. So you can actually create the pull-down and pull-up path diagrams the same way you would create the pull-down and pull-up for the transistor networks. You would just think of it the same way. E, if E is 0, right, it's automatically 0 to 1 regardless. So that's a path. Same thing, here's a path. So then it has to go through B or C, and then through A, right? So it's A and B or C. So this has to be satisfied, and then this has to be satisfied. And so that's how you create the path diagram. From there, we would go to the second stage of here. So you draw the path diagram for the pull-up network. The path diagram for the pull-up network. Here's kind of what this dotted line is. I don't know why they included this diagram this way. So you have B out, and it's going to go through D, and then it has to go through B or C to get to VDD, or it can go through A. Same thing here. It goes through D, and then you can go to A to, this is VDD, that's probably go the other way. D can go through A and then B, right? Or VDD has to go through C, or B, and then D. That's going to be a battle I'm going to fight all semester, isn't it? Yeah, awesome.
Did adapter come loose?
No, it just times out. Sometimes if I just move the mouse, it works fine. Okay, so third stage. This is where I mean by the third stage in terms of drawing the sticks. D, A, B, C. The reason I kept them in this order is because if you look at both path diagrams, you can have D, for example, for VDD, so for the pull-down network, the simplest path is you create contact here, goes across the D transistor here to V out. Right? And then what we're going to do is we're going to go, it has to go through C or B. So it's either going to go here, right, to A, or it's going to go through C and then through A. So we're going to learn here in a second how to actually use metal to create work. But this is just the stage. So when you draw it out, you draw this out, it'll be fine. Everything else is just a contact. So VDD, V out, and ground, they're all metal, so that's blue. So we'll draw this a along with you. So if VDG, ground, so this is out, and this is ground. Okay? So that's blue, and then we're going to use P active is orange, right? We have P active, and then N active is green. And so for poly, choosing the order is basically, you're going to use this based on your path diagram. So you can do D, A, B, C, or D, A, C, B, right? So you want to, first one you're going to want to do for red is D, then A, C, B. So that's how that stage is done. So the next step is we're going to draw the contacts around the poly for the N active based on the pull-down network. So here's the example here. What's going to happen is we're going to take this metal, right? And we're going to create contact with the NL. And then what's going to happen is this portion here represents your D transistor. So you create another contact, and then it goes to the output. So this is going to be, the next step is we're going to create a path that goes through A and B or C that leads us to this metal here. Because this is going to be the A transistor here, this is going to be the B transistor here, and this is going to be the C transistor here, right? So we're going to want it to always go through A, right? So that way we're going to create a contact here. So let me get rid of that metal. It's just the green diffusion area here. You're not going to want to put that. It's going to remain green. So that's why we have the contact. We don't want them overlapping. So the question is, how do we get to B or C? Right? Yep. So what we do is we create a pin here between B and C. Go from metal to here. And so if it goes through C, it's just going to go through this portion, right? If it's B, what's going to happen is it's going to go through the B transistor, around C, through A, and then out. So then what happens is we create the contact here, draw a metal. Does that make sense? So now we're going to do the same thing for the pull-up network. So what's the pull-up network? Here's the path diagram for the pull-up network here on the left. So the path in order to get to B out, it always has to go through D, right? So the first step is we start at D, dot X, so it's going to go through D no matter what. So now we have our next contact here. So now we can do one of two things. You can either go through A and then out, or you can go through B and C and then out. And now here's how we do this. If it just goes through A, it goes straight to the output. Or we circumvent A and then go through C and B. The reason we did it this way is that it allows us to go through B transistor, C transistor. We don't need to create a contact because there's no change in direction, right? And then out.
So we're just trying to make a physical path between
Exactly right.
D street and out.
It's exactly right. This is 1, this is 0, and all you're doing is just creating, you're taking this path diagrams to the NMOS. So this relates to, if we go back to 1.4, all the way up to 1.4 here.
So
This final solution, I'll answer your question in a second, Thomas. This solution here relates, that is physically, this is a stick diagram that allows you to translate this PMOS network from that equation, then you use your design rules to actually fabricate the circuit. So let me scroll back down and then I'll take your question, Thomas. Okay, so this is the final answer of what I expect on the exam. This combination, we can go through I'll ask that question in a second. A really good exam type question is combining this problem and 1.4, the one where you have to start with the equation, meaning the PMOS, and NMOS pull up and pull-down network, and then draw a state diagram. That's a very, in my opinion, that's a very good comprehensive type question because it shows me you understand how PMOS and NMOS transistors work. It shows me that you understand how the actual physical transistor work. You know, show me that you understand contacts. You show me you understand poly. You show me you understand diffusion and NMOS well. You just show me you understand logic. So this is a very good question that should take you about 20 minutes on an exam to do. Bring color pencils. That would be a good investment, especially color pencils before movies. Right? Good in there. I know the pain. But in my opinion, combining 1.4 and 1.6 is a very good exam type question. So, okay, Thomas, what's your question? Oh, I'm sorry, Adam.
Yeah. So when you say go through the B and C transistor, go through the A, that's when the channel opens.
Correct. Mm-hmm. So let's dig a little deeper into what you're talking about. Okay. So we have created an instance where we have. So the logic is, in order to have a 1, going all the way back up here, we have to have not B or not C, right? That's because our PMOSs react strong with zeros. So we have an instance where D, B, and C are all zeros. So now we actually have this PMOS transistor here, we have a channel. Let's say A is a 1, that means it's closed. We can go through here, that means we have the source and the drain, and then the source and the drain from B, and the source and the drain from C. They're both open, we created those channels, and then it goes to the output through the metal, through the contact. That's a good question. Does anybody have any other questions? All right, let me ask you a thought question. Why is this stick diagram here incorrect? Great, sure. Okay. Very common mistakes. Let's see if you guys catch it. You'd be surprised you're working on fabrication. You're like, I don't understand. It was a stupid error. And then after 3 hours, you realize you put in a short. You're like, oh, I'm an idiot. Okay, so we can go through 1.7 really quickly, and this will be the end of today's lecture. So this is 1.7 is kind of the same as combining 1.4 and 1.6. So we start out with not A, B, or D, C, E, right? 1.7. And so we start out, we do the pull-down network. A and B are ANDed, so they're in series. D is ANDed with C or E, right? So then they're in parallel, and they both go to V out. You perform the De Morgan's law. We see that not A or not B. So there's forward series. You're going to have slots C and E. Okay, so then we have D, C, and E. We draw path diagrams. Yeah, hold on. I want to do this on the board. Yeah. Okay, so you have, so the first part is correct. So you have A and B, and then there's C and E are in parallel here. This part's right. And then that's D. And these all go to the output, right? And then we have, if you go to Morgan's, which we've done correctly here, now we score, they're in parallel, and they're in series. So I go here and go A, this is where the mistake is. B, yeah, that's right. Yeah, that's right. And then here, we're going to have B or, so they're in parallel. This part's correct. This is where the mistake is. So, I wish I had my little marker here. Here, it just should be, these two should be in parallel. This probably affects the whole diagram. Yeah, it does. All right, so we're going to stop here. I'm going to redo this problem. So it's 1.6. So it's, okay, so we started, the homework assignment is going to be 1.16 through 1.20, and then 1.4 through 1.6.